The ocean covers 71% of Earth's surface. Its average depth is 3,688 meters. Its deepest point, the Challenger Deep in the Mariana Trench, sits at approximately 10,935 meters below sea level. The total volume of water in the world's oceans is roughly 1.335 billion cubic kilometers. We have mapped approximately 20% of the ocean floor with any meaningful resolution. We have physically explored, meaning sent humans or instruments close enough to observe, sample, and document roughly 5% of it. For comparison, we have higher resolution maps of the surface of Mars than we do of our own ocean floor. That number requires some explanation because it sounds implausible. We've been sailing on the ocean for thousands of years. We have submarines, we have sonar, we have satellites. How is it possible that 95% of the ocean remains unexplored? The answer is not one thing. It's several, and they compound each other.
The first problem is pressure. At sea level, atmospheric pressure is approximately 1 bar, 1 kilogram of force per square centimeter of surface. Every 10 meters of depth adds another bar. At 100 meters depth, it's 10 bar. At 1,000 meters, it's 100 bar. At the bottom of the Mariana Trench, the pressure is approximately 1,086 bar, over 1,000 times the pressure at the surface. This is not a problem that better materials fully solve. It's a fundamental physics problem. Any vessel sent to extreme depth must be either strong enough to resist that pressure or be pressure neutral, meaning the interior of the vessel is flooded, and any equipment inside must itself be pressure resistant. Building structures that maintain a habitable interior atmosphere at 1,000 bar requires materials and engineering that push against the limits of what we can currently produce, and the deeper you go, the more the engineering challenge compounds. The Trieste, the vessel that first reached the bottom of the Challenger Deep in 1960, had a crew sphere with walls 12.7 centimeters thick. The entire descent took 4 hours and 47 minutes. The crew of two, Jacques Picard and Don Walsh, spent approximately 20 minutes at the bottom before ascending. The vessel's observation window cracked during the descent. They completed the dive anyway. Only 3 crewed vessels have ever reached the full depth of the Challenger Deep. By comparison, 12 humans have walked on the moon.
The second problem is light. Sunlight penetrates seawater to a maximum depth of approximately 200 meters under ideal conditions. Below 200 meters is the twilight zone. Some faint light, not enough for photosynthesis. Below 1,000 meters is the midnight zone. No sunlight reaches it at all. It is permanently, completely dark. Everything below 1,000 meters, which is the vast majority of the ocean by volume, must be observed using artificial light. Artificial light underwater has a limited range. Even the most powerful underwater lights illuminate only a few meters in the clearest conditions, and deep ocean water is not always clear. Particulate matter, marine snow, the continuous fall of organic debris from the upper ocean, and bioluminescent organisms scatter and absorb light. This means that deep ocean exploration is done in near darkness, with a very small illuminated field of view, moving through an environment where anything more than a few meters away is invisible. It's the equivalent of exploring a continent at night with a flashlight.
The third problem is money. Deep-sea exploration is extraordinarily expensive. A single deep-sea research expedition using a remotely operated vehicle typically costs between $30,000 and $50,000 per day. A full ocean research cruise deploying a deep ocean ROV costs millions of dollars. The construction of a new deep-rated ROV capable of reaching 6,000 meters costs upward of $5 million. A full ocean depth capable vehicle, able to reach the deepest points, costs significantly more. For comparison, NASA's annual budget is approximately $25 billion. The National Oceanic and Atmospheric Administration, NOAA, the primary U.S. agency responsible for ocean research, has an annual budget of approximately $6 billion, a significant portion of which is dedicated to weather forecasting, fisheries management, and other non-exploration functions. The budget available for actual deep ocean exploration is a fraction of that. The result is a prioritization problem. The ocean is enormous. The tools available to explore it are limited and expensive. Decisions about where to send those tools, for how long, and with what objectives are made in an environment of chronic underfunding. The fourth problem is that the tools we have were designed to solve specific problems, not to comprehensively map and explore. Sonar, sound-based mapping, is the primary technology for surveying the ocean floor from the surface. It works by sending sound pulses downward and measuring the time it takes for the echo to return. The resolution of sonar mapping degrades with depth. Ship-based multi-beam sonar, which is the standard tool for large-scale ocean floor mapping, produces resolution of approximately 100 meters at typical ocean depths. For comparison, satellite imagery of Earth's land surface routinely achieves resolution of less than 1 meter. The Seabed 2030 project, a global initiative to map the entire ocean floor by 2030, has made significant progress since launching in 2017. As of recent surveys, approximately 24% of the ocean floor has been mapped to modern standards. The remaining 76% has either never been surveyed or was surveyed using older, lower-resolution methods. Mapping the floor and exploring it are also two different things. Sonar tells you the shape of the terrain. It tells you nothing about what lives there, what the sediment composition is, what chemical processes are occurring, or what structures exist below the surface of the seafloor itself. That requires physical presence, either human or robotic.
The 5% we have explored has produced a consistent pattern. Everything we find suggests the remaining 95% contains things we don't expect. In 1977, researchers exploring the Galapagos Rift in the Pacific found hydrothermal vents, cracks in the seafloor where superheated water rich in minerals emerges from beneath the Earth's crust. Around these vents, in complete darkness, under enormous pressure, with no sunlight and therefore no photosynthesis, they found entire ecosystems. Tube worms up to 2 meters long, clams the size of dinner plates, shrimp with no eyes, microbial mats covering the seafloor, an entire food chain based not on sunlight, but on chemosynthesis, microbes that derive energy from the chemical reactions of the vent fluids. Before 1977, the scientific consensus was that life in the deep ocean was sparse and dependent on organic matter drifting down from the surface. The hydrothermal vent ecosystems overturned that consensus entirely. They also opened a serious scientific conversation about the possibility of life on other planets, specifically on moons like Europa and Enceladus, which are believed to have liquid oceans beneath their ice surfaces, potentially with hydrothermal activity. In 1987, the Black Smoker hydrothermal vent system known as Lost City was discovered on the Mid-Atlantic Ridge. It produces towering carbonate chimneys, some over 60 meters tall, and hosts microbial communities that survive in conditions previously considered life incompatible. Lost City was discovered by accident when researchers were looking for something else. In 2004, the coelacanth, a fish thought to have gone extinct 65 million years ago with the dinosaurs, was filmed alive in a submarine canyon off the coast of South Africa at around 100 meters depth. It had first been rediscovered in 1938, also by accident, by a museum curator examining a fishing catch. A fish that supposedly didn't exist had been living in waters adjacent to a populated coastline for millions of years without being documented. New species are discovered on virtually every deep-sea expedition, not occasionally, routinely. A 2023 survey of a previously unexplored seamount chain off the coast of Chile documented over 100 new species to science in a single expedition. Many of them were not subtle variations on known species. They were genuinely new body plans, new adaptations, new organisms that fit nowhere in existing taxonomies without revision.
The ocean regulates Earth's climate. It absorbs approximately 90% of the excess heat generated by climate change and approximately 25 to 30% of the carbon dioxide humans produce. The processes by which it does this, ocean circulation, biological carbon pumps, deep water formation, are not fully understood. Our climate models are built on incomplete data about systems we have not fully mapped or observed. The deep ocean also contains mineral deposits, polymetallic nodules on the seafloor containing manganese, cobalt, nickel, and copper that are now being considered for deep-sea mining. There are active licensing agreements for exploration. The environmental baseline for these ecosystems, what lives there, how the communities are structured, what the impact of disturbance would be, is largely unknown because the ecosystems haven't been studied. We are making decisions about extracting resources from environments we have never looked at. The 5% figure is not a historical artifact, something true once that will be corrected soon.
At current rates of exploration and funding, comprehensive deep ocean exploration is not a near-term prospect. The ocean is simply too large, too deep, too expensive to access, and too low on the list of institutional priorities. What's down there has been accumulating for 3.8 billion years. We started looking about 60 years ago. We've seen 5% of it.